Welcome to the course on an introduction to coding theory. I am Adrish Banerjee, and today we are going to talk about automatic repeat request schemes. So this is the outline of the talk today. I am first going to briefly describe what is an ARQ scheme, and then I'll talk about the role of error detecting codes in ARQ schemes. Subsequently, I will be talking about three different protocols for retransmission that we are going to use, and then I am going to analyze the performance of those three protocols, and I am going to analyze in terms of efficiency of those protocols as well as reliability of those ARQ protocols. And finally, I am going to talk about hybrid ARQ, which is a combination of forward error correction and automatic repeat request schemes. So if you recall, in the first lecture we talked about there are two possible strategies for error correction. One is forward error correction. So channels which are one way, so for example there is only one way communication from transmitter to receiver. So in those schemes, in those kinds of channels, we used forward error correction schemes. Now what do we do in forward error correcting schemes? So we encode our information sequence using an error correcting code and send it over the communication link. The receiver will try to detect and correct errors based on the redundant bits that we have transmitted. If the packet is not received correctly in a forward error correcting scheme, there is no mechanism for receiver to let the transmitter know that it has not received correctly, because it is a one way channel. And the error correcting codes used in these channels are known as forward error correction codes. Now channels where there is a feedback from the receiver to the transmitter, so the receiver, if it receives a information sequence, we can encode the information sequence using an error correcting code, which we will use for error detection. Now once we transmit this packet to the receiver will try to detect if there is a parity violation. Now if the receiver is able to detect that the bits are not received correctly, the receiver is going to send a negative acknowledgement to the transmitter, because it is a two-way channel. So through this feedback channel, the receiver will inform the transmitter that it has not received the packet correctly, and then the transmitter will retransmit the packet. Now if the packet which was transmitted is received error free, then the receiver will send an acknowledgement saying I have received the packet correctly, and then the transmitter will send a new packet. So in a two-way communication channel, there exists a feedback path from the receiver to the transmitter, and the error correcting codes that we use for such communication channels are known as automatic repeat request, which is also known by this acronym ARQ. Now what is the role of error detecting code in ARQ schemes? So an automatic repeat request schemes uses an error detecting code to find out whether the packet that we transmitted over the communication channel, whether the packet has been received correctly or not. So what we do at the transmitter is we encode these information sequence using an error detecting code, and we transmit over this communication channel. Now at the receiver, this error detecting code will try to find out whether the packet has been received correctly or not using those additional parity bits. Now one of the most commonly used error detecting codes in ARQ application is what is known as CRC, cyclic redundancy check codes. CRC codes are error detecting codes which are very popularly used for ARQ applications. So what is done is we encode our information sequence using this CRC codes and send it over the communication channel, and then using those additional parity bits at the receiver we will try to find out whether the bits have been received correctly or not. So it is a NK code, linear block code. So block size is, code length is n, information sequence length is k, so number of parity bits is n minus k. So a CRC code is defined by a generator polynomial of degree n minus k, which is number of parity bits that we are using. So let the n bits in a frame. Now we are going to use interchangeably the word packet frame. Essentially we are sending a block of n bits. So let us denote the block of n bits by Cn minus 1, Cn minus 2, Cn minus 3, C1, C0. So this is a block of n bits, and let the n minus k low order bits, that means from C0 to Cr minus 1. What is R? R is essentially my n minus k. Okay. So let us assume that the low order n minus k bits are my parity bits. So then in CRC code the parity bits are chosen in such a way such that this code polynomial is divisible by the generator polynomial of the CRC code. So we are going to choose this C0, C1, C2, C3, Cr minus 1 in such a way such that this code polynomial Cx is divisible by this generator polynomial of the CRC code of degree n minus k. Now let us take an example to illustrate this, and remember when we are talking about so this code polynomial as well as this generator polynomials, they are polynomials with binary coefficients. So we are talking about all binary operations. So these operations are defined over modulo 2. Let us take an example of a CRC code. So we consider a CRC code which adds 4 parity bits whose generator polynomial is given by x to the power 4 plus x plus 1. So this is a generator polynomial for CRC code, and our NK code parameters are given by 15, 11. So n is 15 and k is 11, and there are 4 parity bits. So let us assume those 11 information bits are given by this 1 0 0 1 1 0 0 0 1 1 0. So these are the 11 information bits. Now we want to encode these information bits using a CRC code which will add 4 parity bits whose generator polynomial is given by this. Gx is x4 plus x plus 1. Now remember, we need to choose 4 parity bits in such a way such that this code polynomial c of x is divisible by this generator polynomial g of x. So we are going to write this information sequence in this polynomial form. So this is my C14, C13, C12, C11, C10, C9, C8, C7, C6, C5, C4, and then C3, C2, C1, C0. These are my parity bits. So remember, this is x14 plus x11 plus x10 plus x6 plus x5 plus C3 x3 plus C2 x square plus C1 x plus C0. This is my code polynomial. Now I need to choose this C3, C2, C1, C0 in such a way such that this code polynomial C of x is divisible by g of x, this generator polynomial for this CRC code. So, in this case we can verify that if we choose C3 and C1 to be 1 and C2 and C0 to be 0, then this code polynomial is divisible by g of x. And we can see that in this case, if we choose our C3, C2, C1, C0 in this fashion, our C of x is divisible by g of x, and this is basically product of g of x into x to the power 10 plus x square plus x. And this is a unique choice of these priority bits C0, C1, C2, C3, which will ensure that C of x is divisible by g of x. Now, at the receiver, what we are going to do is, once we get this receive polynomial, we are going to check whether there are errors or not. How are we going to check? We are going to divide this receive polynomial by g of x. If it is divisible by g of x, that means there are either no error or it has converted to some other code word and the errors are undetected. Okay. Now, if this receive polynomial is divisible by g of x, then we declare that the frame is error free, or else if it is not divisible by g of x, we know that there is an error in the receive sequence. So, this is how we are going to make use of this CRC for error detection. I have listed some of the popular CRC codes. So, this CRC12 code, its generator polynomial is given by this x12 plus x11 plus x3 plus x square plus x plus 1. The maximum n that it can handle is 2047 and its minimum distance is 4. So, it can detect 3 errors. Another popular code is CRC NC code, which has this is a 16-bit CRC code, generator polynomial given by x16 plus x15 plus x square plus 1, and can handle n of 32,767. Its minimum distance is also 4. Another 16-bit CRC code which is popular is this CRC CCITT code, and again its generator polynomial is given by s16 plus x12 plus x5 plus 1. Its minimum distance is also 4 and it can take maximum n of 32,767. So, if you subtract from these n the number of priority bits, in this case it is 12, in this case it is 16, in this case it is 16, you will get the size of the information sequence that you are encoding using these CRC codes. Now that we have explained what is an ARQ scheme and the role played by error detecting code, let us talk about what are the different protocols that we can employ when a packet is detected to be in error. What are the different ways in which we can do retransmission? So, as you know, in ARQ protocols, if the frames are received in error, we need to retransmit those frames or packets. So, we are going to talk about 3 different protocols for ARQ. The first one is called stop and wait. The second is known as go back n, and the third is known as selective repeat ARQ scheme. We are going to talk about each one of them in detail, and we are also going to do performance analysis of each of these ARQ protocols. Now, the way these ARQ protocols work is basically if the packet is received is error free or there are undetected errors, the receiver is going to send a positive acknowledgement to indicate that the packet has been successfully received. Otherwise, it is going to send a negative acknowledgement and transmitter is then going to retransmit some packet. Okay. Now, when we are sending this acknowledgement and negative acknowledgement from the receiver to the transmitter through this feedback channel, we assume that these have been protected using some error correcting and error detecting code. So, in all the analysis we will assume that there is no error in sending these acknowledgement and negative acknowledgement signals from the receiver to the transmitter. We will also assume that if the transmitter does not receive acknowledgement or negative acknowledgement in time, so there is a timeout. So, we fix up a time. If we receive an acknowledgement or negative acknowledgement of a packet that we have transmitted, after we have transmitted that packet, if we do not receive an ACK or a NACK within a particular time instance, we will assume that the packet has not been successfully received. Okay. So, if ACKs and NACKs are not received in specified amount of time, the transmitter adopts a timeout strategy where it will assume as if the frame is not correctly received. The another assumption that we are going to make is that all the frames that we transmit over the forward link as well as the acknowledgements that are sent over the reverse link, they are all received in order. So, they are all received in order. So, the packets that we are sending first, the receiver is going to receive them first, the transmitter is going to receive the NACK and ACK of those packets first which have been transmitted earlier. That is what I mean when I said all are received in order. So, if I send packet number 1 first, 2 first and 3 first, the receiver will also receive packet 1 first, then 2 and then 3. And similarly, the transmitter will first receive the NACK or ACK of packet 1, then NACK and ACK of packet 2 and then NACK or ACK of packet 3. That is what I mean when I say all are received in order. We also assume that there is no undetected error in the feedback channel. So, the NACK and ACK that are sent are received correctly by the transmitter. Now, let us talk about each of these protocols in detail. So, the first protocol that we are going to talk about is known as stop and wait ARQ. So, as the name suggests, we transmit the packet and wait until we get acknowledgement of that particular packet of the frame. So, in stop and wait ARQ, the transmitter waits until it gets an acknowledgement of the sent frame before sending a new frame. So, in stop and wait ARQ protocol, we are going to send a packet, the receiver is going to receive it, it is going to detect depending on whether the packet is received correctly or not, it is going to send back to the transmitter an acknowledgement or negative acknowledgement, and based on that the transmitter will now send either a new frame or a packet or the same packet if it is not received correctly. So, if NACK is received, the same frame is retransmitted, else a new frame is transmitted. So, in this protocol, the transmitter and the receiver take turns in sending frames and acknowledgement. So, the transmitter is sending a packet, is sending a frame to the receiver, receiver is sending an ACK or a NACK to the transmitter back. And to avoid potential confusion caused by lost frame, there is a sequence number often included in the header of the frame that we are sending. Similarly, there is a sequence number embedded in the negative or positive acknowledgement, so that the transmitter knows which packet has been received correctly or not. So, in this diagram I have shown how this stop and wait ARQ works. So, this is my transmitter, this is my receiver. So let us say it transmits frame number 1. Okay. Now, there is some propagation transmission delay. So, basically after some time the receiver receives this packet 1. and using this CRC code it detects whether the packet is in error or not. So in this case packet is not in error, so it sends a positive acknowledgement. So it sends an acknowledgement to the back to the transmitter. At this time instance the transmitter has received an acknowledgement of frame number 1. So now it is going to send frame number 2. Again after some delay this frame number 2 is received at this receiver. Receiver will employ CRC check to find out whether there is any parity violation. In this particular example there is a parity violation, so the receiver sends a negative acknowledgement to the transmitter. Now after this time delay this transmitter receives at this time instance a negative acknowledgement, that is the packet 2 or the frame 2 is not been received correctly. So what does the transmitter do? It retransmits packet 2. And again after some delay this packet is received at the receiver. This time this is received correctly, so the receiver sends an acknowledgement. After some time propagation delay this acknowledgement is received at the transmitter. Since it is a positive acknowledgement the transmitter will decide to send a new frame, in this case frame number 3. So this process continues. This frame is received here after some time delay, this is received correctly, so it sends an acknowledgement. Next the transmitter is going to send a packet number 4, this packet is received here, again this packet is received correctly, so the receiver will send an acknowledgement which is received at the transmitter at this time instance. So the transmitter decides to send packet number 5 which is received at the receiver after some delay. Now this packet is not received correctly, so the receiver is going to send a negative acknowledgement to the transmitter, and after some time delay this negative acknowledgement is received at the transmitter. Since it is a negative acknowledgement the transmitter will decide to send the same packet again. So you can see there is an idle time involved here for the transmitter. It sends a packet and wait for this round trip delay until it gets back acknowledgement or negative acknowledgement from the receiver. So clearly from the point of view of efficiency this does not seem to be a very good scheme. Why? Because you are transmitting for a very small time, but then you are, for this idle time you are not sending any packets. But from the implementation point of view this is pretty straightforward and simple, because you are sending a new packet only when you are sure that the packet that you sent earlier has been received correctly. So this is your stop and wait ARQ. Now as I said, the problem with stop and wait ARQ is you send a packet, you wait for it to receive its acknowledgement before you send the next packet. So you have this large idle time, possibly large idle time. So this problem has been solved in go back and ARQ protocol. So unlike stop and wait ARQ, in go back and ARQ the transmitter does not wait for an acknowledgement before sending another frame. Okay. So it is like a sliding window kind of protocol. So you can send packet number 1 to n, let us say, okay, and in the meantime you send packet 1, 2, 3, 4, 5 up to n. Now you will send packet number n plus 1 only when you would have received the acknowledgement for packet number 1. You are going to send packet number n plus 2 only when you get acknowledgement for packet number 2. So we send a block of frames or packets, okay, in this particular scheme. We do not wait for each individual packets acknowledgement or negative acknowledgement to reach receiver. We are sending a block of packets, you can say. Now if the first packet or first frame in this window is acknowledged to be received correctly, what the transmitter does is transmitter slides this window one position, dropping the acknowledged package or the frame and then adding a new frame that is then transmitted. Now what happens if the first frame is in that window is negatively acknowledgement, that is it's not received correctly, then the transmitter backs up and resends all the frames in the window starting from the erroneous received frame. So for example, if I am sending packet 1 to n and my fifth packet is in error, I get a NAC corresponding to fifth packet, then fifth onward I am going to start sending those packets again. So this go back n is often referred to as sliding window protocol because the transmitter maintains a sliding window of active frames that have been transmitted and for whose acknowledgement it is basically waiting to get the acknowledgement for those frames or packets. Now as you can see here, this window size or the sliding window size n is crucial because we do not want a very special case of n equal to 1 is stop and wait, and the other extreme is if n is too large, then of course that is also not good. So we need to choose appropriately what n is depending on what is the propagation delay of the system or what is the length of the frames that we are sending. Now I am illustrating go back n protocol using this diagram. So in this case I am taking n to be 7. So you can see here I am sending this frame of 7 bits 1, 2, 3, 4, 5, 6, 7. I am sending these frames. Now what happens is this frame number 1 after some delay is received at this time instance. Now the receiver again will apply CRC check and will try to find out whether there is any parity violation or not. If CRC code detects any error, it will send a negative acknowledgement, otherwise it will send a positive acknowledgement. So in this case this packet 1 was received correctly, so a positive acknowledgement was sent. Now there is a delay in receiving this positive acknowledgement, so at this particular time instance the transmitter receives a positive acknowledgement about frame number 1. Remember I said here we are sending a block of n bits. Now we are going to send n plus 1 frame only when we get the acknowledgement about frame number 1. So at this time instance we are getting an acknowledgement of this frame number 1. So this is an acknowledgement, so we are going to send packet number 8. Now in the meantime the second packet was sent and this was received correctly. So at this instance we get the transmitter gets an acknowledgement that the second packet has been received correctly. So it transmits a new packet which is packet or frame number 9. Next this 3 has been received. Now this 3 has been received in error, so this receiver is going to send a negative acknowledgement. So receiver sends a negative acknowledgement which is received at the transmitter at this time instance. Now since this is a negative acknowledgement, as I said, if you get intimation about a incorrect frame received, the transmitter is going to back off and start sending again from the packet which has been erroneously received. So in this case the third packet was not received correctly, so we will start sending again from packet number 3. So at this time instance I am going to send packet frame number 3. Okay. Now similarly you get a 4 here which is received correctly, so you send now the next packet after 3 is 4. So like that basically we are going to send next 7 bits 3, 4, 5, 6, 7, 8, 9 we are going to send. So in go back n what we do is whenever we receive a packet in error we start retransmitting from this packet. So in this case we receive packet number 3 in error, we start retransmitting from packet number 3, 4, 5. So it may so happen that earlier we sent packet number 1 to 7, 4, 5, 6 might have been received correctly, but we ignore them. We again retransmit the packet. So in terms of efficiency, this is still not very good because we are retransmitting some packets which we might have received correctly. So the other extreme is what is known as selective repeat ARQ. So in this case, when a frame is received in error, we are only going to send those frames which have been received in error. So unlike go back n, in go back n what were we doing? If a packet number I was received in error, we start retransmitting again from packet I, packet number I plus 1, I plus 2, I plus 3. But in selective repeat, if a packet I is not received correctly, we are only going to retransmit packet I. We are not going to retransmit packet I plus 1 or I plus 2 if they were received correctly. Okay, so we are selectively only retransmitting those packets which are not received correctly by the receiver. What is the drawback of this system? Now, since we are only selectively asking for retransmission of only those packets which are in error, we need to maintain some buffer so that once we receive those erroneous packets, we can put them back in the right order and deliver it to the intended receiver. Okay, so the drawback of selective repeat system is one has to store these arriving frame in a buffer and reorder them in the correct order so that they are delivered to the recipient in the correct order. So you can see here, so you have, so this is my transmitter, this is my receiver. Okay, so you send packet 1 is received correctly, so you send an acknowledgement. So you are sending packet 1, 2, 3, 4, 5. Now here you received an acknowledgement for packet number 1, so you send next packet, which is packet number 6. Here you are receiving an acknowledgement for packet number 2, you send the next packet 7. In this case, packet number 3 was received in error, so you at this time instance you are getting a negative acknowledgement of this packet number 3. So what this transmitter will do is it will retransmit packet number 3. Now note the difference from go back n. In go back n, what we would have done was we would have started retransmitting packet 4, 5, 6. Here, since packet 4 is received correctly, we don't retransmit it. We send the next packet. We already sent up to packet 7, so now we are going to send packet 8. So this is a difference from go back n. In go back n, we start retransmitting again from the incorrectly received packet. Now here you get an acknowledgement for packet number 5, so you send the next packet, which is packet number 10. Now here you receive acknowledgement for 6. So look at this example again. So the 7th frame was not received correctly, so you send a negative acknowledgement. So at this instance, the transmitter received a negative acknowledgement. So what you are going to do is you are going to insert this frame number 7, which was incorrectly received, here and continue. Subsequently, you received an acknowledgement about the packet that you sent, so you send the new packet, packet number 11. So you can see in selective repeat ARQ, we are selectively retransmitting only those packets which are not received correctly. So you can see here, I am receiving packet number 3 here correctly because this was not, actually received packet number 3 here correctly at the receiver because this was not incorrect. In the meantime, I already received correctly packet number 1, 2, 4, 5, 6, 7. So once I get packet number 3 or frame number 3, I need to put it back in the order after packet number 2 and before packet number 4. So that's what I meant. At the receiver, you need to keep buffer to save or store all the packets that you have received before this packet number 3 was received. So 4, 5, 6, 7, you need to store them in the buffer, and once you get packet number 3, you put it back in the order after packet number 2. So these are the 3 protocols you can see. Stop and wait, very inefficient but very simple protocol. Selected repeat, from the efficiency point of view, very good, but from the complexity point of view, the most complex. And go back and is a in between. I mean, efficiency is poor than selective repeat, but then it's easier than selective repeat request scheme. So now we are going to talk about performance evaluation of these ARQ protocols. So first thing that we are going to talk about is reliability of these ARQ schemes. So how can we evaluate the reliability of these ARQ schemes? We can evaluate their reliability using frame error rate. So when you send a packet and the packet is received in error, we say the frame or the packet is in error, right? So what we are doing is we are sending this coded sequence into small blocks of data which are known as frames or packets, and a frame error happens if any of the information bit in that frame is in error, and the percentage of frames which are in error is known as frame error rate. So that's a decoding frame error rate is a percentage of frames in error. Now what happens when we are sending a frame? What happens when a transmitter sends a frame? So there are 3 possibilities. The first possibility is the frame is received correctly. So there has been no transmission errors, whatever we sent, exactly the same thing is received. So the frame is received error free. Second possibility is frame is received in error and the error detecting code that we are using is able to detect that there is an error. So that is option number 2. And the third option is frame is received in error, however the error detecting code that we use is unable to detect that error. So when does this situation happen? We say that an undetected error has happened, and an undetected error happens if the transmitted code word gets transformed into some other code word. So the error pattern is such that it transforms one code word to some other code word, and then we would not be able to detect the error. So that's the third possibility. So let PD be the probability that a frame is received in error and it is correctly detected by the error detecting code, and let PU be the probability that a frame is received in error but the error detecting code is unable to detect it. Now we are trying to find out an expression for frame error rate for these ARQ protocols. So let us assume there is no limit on retransmission. So whenever we get a negative acknowledgement, we will ask for retransmission. So when does a frame error occur? A frame error occurs if we accept a packet which is in error, but the error detecting code is not able to detect those errors, and that probability is given by PU. Okay. So it can happen that the first time that we send the packet, the error detecting code is not able to detect the error and it accepts the packet. So this is given by this probability. Or it may happen that first time instance it was able to detect the packet, but when we retransmitted it for the first time, the error detecting code was not able to detect the error. So that probability is given by PD times PU. Or it may so happen that 2 times we were able to correctly detect the error, but the third time we were not able to detect the error. So that probability is given by this. Similarly, we can write this PDQ PU plus PD4 PU like that. So this can be written in this form, which is can be written as a geometric series. So we can be written as PU divided by 1 minus PD. Now this is true for any ARQ protocol. Now, so the frame error rate depends on PU and PD. So PD is a probability that it's able to correctly detect that the frame is in error. So that depends on the error detecting capability of the error detecting code that we are using. Similarly, this undetected error probability is also related to the weight distribution of the error detecting code that we are using. In fact, we have when we talked about linear block code, we talked about what's the probability of undetected error, because we have been dealing with linear block codes. So if you are sending all 0 code words and what we receive is a non-zero code word, then there's an error. So we can use the weight distribution of a linear block code to find out the probability of undetected error. So you can see that frame error rate performance of this ARQ protocols does not depend on what we are transmitting, how we are transmitting. It only depends on the error detecting code that we are using. So to summarize, reliability of an ARQ protocol, which we are determining on the basis of frame error rate, depends only on the error detecting capability of the underlying error detecting code, and it is independent of how these corrupted frames or packets are subsequently retransmitted. Next, we are going to move into the efficiency analysis of this ARQ protocols. So how are we going to measure the efficiency of this ARQ scheme? So we are going to do that on the basis of throughput that we can achieve when we are using these ARQ protocols. And this efficiency is very closely related to what sort of protocol that we are using. As you can see, we saw in stop and wait, for a very long time, idle time, we are just waiting, we are not transmitting anything, so this efficiency is very low. On the other extreme, the selective repeat has the best efficiency because we are only retransmitting those packets which are received incorrectly. So we are measuring or we are quantifying the efficiency of an ARQ scheme using its throughput. So the throughput of an ARQ scheme is defined as the ratio of the average number of information bits accepted by the receiver per unit time to the number of bits that can be transmitted over the channel per unit time. So let us compute this throughput for each of these three ARQ protocols that we talked about. So first scheme that we are going to talk about is selective repeat ARQ. Now in a selective repeat ARQ, the probability of receiving or accepting a packet is given by P, where P is the probability that P is sum of two probability. This probability P sub C is basically the probability that the frame is delivered error free, and this probability PU is the probability that the error detecting code failed to detect an error. So we are going to accept a packet either when it is received error free or the error detecting code failed to detect an error and it thinks that it has received the packet correctly. So this probability P, which is sum of these two probability, is with this probability we are going to accept, the receiver is going to accept a particular packet in SR ARQ scheme. Now T sub SR is a random variable that we are defining, which is equal to the number of frame transmission required for a selective repeat ARQ scheme until a particular frame is accepted. So this is basically a random variable because it can happen that at first instance the packet is accepted, or it can happen that we need to transmit the packet twice to get the packet accepted, or we could have to transmit thrice or more. So T sub SR is a random variable which denotes the number of frame transmission required for selective repeat ARQ until a particular frame is accepted. Now let us compute the probability that TSR is 1. So what is the probability that at first transmission itself you are going to accept the packet? Now we just saw that probability is given by P, which is sum of P sub C plus P sub U. So with probability P, we are going to accept the packet the first transmission. Now what is the probability that we need to transmit the packet twice? So that would be given by 1 minus P, because in the first instance we did not accept the packet, that probability is given by 1 minus P, and the second instance we accepted the packet. So that probability is given by P times 1 minus P. Similarly, what's the probability that we have to make 3 transmissions before a packet is accepted? Now in this case it means that in the first 2 transmissions we did not accept the packet, that probability is 1 minus P square, and the third transmission we accepted it, so that is P 1 minus P square. So we can see that this random variable has a geometric distribution, and the expected value of this is given by 1 divided by P. Now remember, we are using an NK linear block code. We have K information bits and then N minus K CRC check bits, and overall block length is N. So the receiver accepts K information bits in the amount of time it takes to transmit N into expected value of this. So receiver is accepting K information bits over the time it takes to transmit N divided by P over the communication channel. So the throughput is given by K divided by N by P, which is this. So for a selective repeat ARQ scheme, the throughput is given by K by N into P. Now let us compute the throughput for go back N. Again here P sub C denotes the probability that the frame is being received error free at the receiver, and PU denotes the probability that the frame is in error but the receiver is unable to detect it. So a packet will be accepted with probability P. Now here for the analysis we are considering the worst case scenario. And what is the worst case scenario? So we are assuming that the error happens in the beginning of the block. So if the error happens in the beginning of the block, then we need to remember in go back N we backtrack and start sending retransmit the packet from the sequence which has been received incorrectly. So the worst case scenario would be if at the start of this window we receive the first packet itself incorrectly, then we would retransmit the next N bits. So TGBN denotes a random variable which is equal to number of transmissions required in go back N until a particular frame is accepted. Now we are considering a worst case scenario, and what is that worst case scenario? We are assuming that a full window of N frames must be retransmitted every time a frame is rejected. So we are assuming the worst case scenario that the first frame in this window itself is received incorrectly. So we are retransmitting all those packets. So now you can see if the packet is received correctly in the first instance, that probability is 1 into P. Now if the packet is not received correctly first instance, we are retransmitting, because we are considering the worst case scenario, we are retransmitting these N packets. So the number, so we second time it will be received correctly is N plus 1 into, this is the probability that it was not received correctly in the first instance, and this is the probability that in the second instance it was received correctly. Similarly, what's the probability that TGBN is 3? So the first 2 transmissions we did not receive the packet correctly, but in the third transmission received correctly. That probability is given by this, and number of frames that we transmitted is 2 raised to power 2 into n plus 1. So this, like this we can compute, and this expected value comes out to be this quantity, which is 1 plus n into 1 minus p divided by p. Now remember, the receiver is accepting k information bits in this amount of time where it takes to transmit this many bits over the channel. So the throughput of go back n is given by this expression. Now this quantity is less than what we can achieve from selective repeat scheme. And finally we do this analysis for stop and wait ARQ. So let beta denotes the amount of time the transmitter is idle, and this idle time we are measuring in terms of this frame units or frame length. So if a frame is accepted for the first time, the total delay is 1 plus beta frame unit. If the frame is rejected and accepted second time, then the delay is 2 times 1 plus beta. If the frame is rejected second time and accepted third time, the delay is 3 times 1 plus beta. So if we use this random variable t sub SW to represent the delay in terms of this frame unit, then expected value of this is given by, so this is the delay involved when the packet is accepted for the first time, and this is the probability with which the packet will be accepted, the frame will be accepted for the first time. If it is rejected the first time and second time it is accepted, this is the delay, and this is the probability of the frame being rejected first time but accepted second time. Similarly, this is the probability that the frame has been rejected twice, but at the third instance it has been accepted, and this is the corresponding delay. So like that, if you write it, expected value of this TSW comes out to be 1 plus beta divided by p. And again, so the receiver is receiving k bits over the time n times 1 plus beta by p. So the throughput will be given by this expression. Now if we compare the efficiency of stop and wait, go back n and selective repeat ARQ, selective repeat ARQ will give us the best throughput, followed by go back n and then stop and wait. However, from the complexity point of view, stop and wait is the simplest, then go back n, and then the most complex scheme is selective repeat ARQ. So next we are going to talk about hybrid ARQ, which combines forward error correction with ARQ. So as you know that channels, one-way channels we use forward error correction, and in two-way channels we can use ARQ. In a pure ARQ protocols, we send uncoded packets along with some parity bits which we use for error detection. Now in hybrid ARQ, we are using FEC coded packets for transmission. So at the receiver, we will first try to correct the errors and then we will detect for errors. Now if the packets are detected to be in error, the receiver will send a NAC and another packet will be retransmitted. So the difference between ARQ and hybrid ARQ is, in pure ARQ protocols we send uncoded packets along with some parity bits which we use for error detection. So typically in pure ARQ protocols, the information bits are coded using an error detecting code. Here we are encoding the packet using an error detecting as well as error correcting code. So in hybrid ARQ protocols, we encode the transmitted data for both error correction as well as error detection. receiver detects a error, after decoding it will send a negative acknowledgement and then the data will be again transmitted. So hybrid ARQ schemes can be classified into two categories. First one, which is known as type 1 hybrid ARQ scheme, and second one, which is known as type 2 hybrid ARQ schemes. So we first describe type 1 hybrid ARQ scheme. So simple implementation of a type 1 hybrid ARQ scheme is as follows. We use a very high rate error detecting code and a lower rate error correcting code. Now this high rate error detecting code could be like, for example, CRC, which we are going to use to detect error, and this lower rate error correcting code could be your convolutional codes, turbo code, LDPC codes. So the information sequence is first encoded using an error detecting code and then using a error correcting code. At the receiver, when you receive this coded packet, you first try to decode and try to correct errors. So at the receiver, the error correcting code first tries to reconstruct the information sequence or estimate the information sequence, and then it passes that information to the error detecting code, which is going to check whether the estimated information sequence is an error or not. If the error detection code observes that there is a priority violation, for example, if you are using a CRC, we know that the receipt polynomial should be divisible by the generator polynomial of the CRC code. So if the error detecting code observes a priority violation, then it will ask for retransmission. Otherwise, the packet would be assumed to be received correctly and we will accept the packet. And usually in this type 1 ARQ scheme, when we retransmit, we are again sending the same coded packet. So whenever the receiver is asking for retransmission, we are sending the same coded packet again. The receiver tries to correct the errors, and then the information, estimated information sequence is passed to a error detecting code, which will try to detect whether there is any error in the decoded sequence. If there is a error, again receiver will send a NAC and same coded sequence would be sent again. Now type 2 hybrid ARQ scheme works on the principle of incremental redundancy. So what happens here is, you first send information sequence coded using an error detecting code. Alright. Now once you receive this packet, the error detecting code will try to see if the packet has been received correctly or not. Now if the error detecting code does not find any error, or it passed the parity check constraint checks, then the packet will be accepted. Otherwise you will the receiver is going to send a negative acknowledgement, and then the transmitter is going to send a new packet. And what is there in this new packet? That's where the difference lies. So the new packet that we will send will have some parity bits based on the information sequence. Now if you remember, during initial transmission we are sending only the information sequence coding using error detecting code. Now if that is not received correctly, in the first retransmission we are going to send parity bits corresponding to those information bits, and we will encode them using error detecting code and then transmit over the communication channel. Now at the receiver, you already have the information bits that you received in the first transmission. Now you are receiving a parity bit. So the receiver, you can make a more powerful lower rate code, and the decoder can now try to correct the errors. So the difference here is, in type 2 hybrid ARQ scheme, each time when we retransmit, we send new set of parity bits, and at the receiver we are adding these new set of parity bits to our original receive sequences to create a more powerful lower rate code. In type 1 kind of schemes, you are sending coded packets, but then when you are retransmitting, you are sending the same coded packet. There also, if you want, you could combine those packets together to get a better performance, but the difference here is when we are retransmitting in type 2 hybrid ARQ scheme, each time instance we are sending a new set of parity bits. So, the original receipt packet which was received in error is now stored in a buffer and is augmented with newly received parity bits to form a more powerful lower rate forward error correcting code. So, if you take an example, let us say I have a rate 1/3 code. Okay. So, let us say this is my block of information bits. Now, if I pass this block of information bits through a rate 1/3 encoder, what you will get? I will get 3 sets of. Let us assume this is a systematic code. So, this is nothing but this and this are same. These are information sequence, and these are my parity sequence. Now, in type 2 hybrid ARQ scheme, you are sending these information sequence first. Now, if the error detecting code finds out that these information bits are in error, in the first retransmission, you are going to send these parity bits. Now, at the receiver, what you are going to do is, you already had these information bits that you received at the first transmission. Now, to that you add this parity bit. So, now what is going to happen is, you are now effectively creating a rate half code at the receiver, and now this rate half decoder will try to correct errors. Now, if this fails, again you will ask for, the receiver will ask for retransmission, then the transmitter is going to send you another set of parity sequence which is different from what was sent earlier. So, this new set of parity sequence is now sent here. Now, your code has become a rate 1/3 code. So, in type 2 hybrid ARQ scheme, what you are doing is, at each retransmission you are sending new parity bits, and at the receiver you are adding them to already received information sequence and parity sequence and making it a more powerful lower rate code. So, this is how a type 2 ARQ schemes work. Okay. So, with this I am going to conclude my discussion on automatic repeat request schemes. Thank you.